Hey y'all, this lesson is on using the sampling distribution of the sample mean to discover the central limit theorem and talk about its properties. So if you'll remember the sampling distribution of the sample mean, lots of sample, basically what's happening is you have a sample and then you're pulling samples of the sample to create new samples, and it's called a sampling distribution. So it's a lot of like using the same word over and over again, but you're creating this new distribution based on samples of this sample. And we found some really cool stuff with that. I talked about, we had a basketball team and we were looking at their heights, and you can go back and watch that video, but it was a really neat lesson. So some other things that we need to talk about is, if you recall, the variable X of a population that is normally distributed with a mean of mu, so that's a population mean, and a standard deviation of sigma, then the samples of size n, the variable X is also normally distributed with a mean of mu and a standard deviation of sigma over square root n. Okay, that's a lot of words, but this is just a review of what we've already discovered. And this is basically saying that if if we're talking about a sampling distribution, then the sampling distribution of a sample mean will have the same population mean, but the standard deviation will be adjusted by dividing by square root n. And that's review. If that's not making sense to you, then just make sure you go back and watch that video. And also remember that for a sample to be considered large, remember it has to be greater than or equal to 30. And that's going to play into what we're looking at today. So for this lesson, I used an applet, is what they call it. So with my textbook, there was an applet, and you could run these simulations. And instead of doing that, to save some time, I grabbed screenshots of the experiments that I ran with the applet. And so you can kind of see where I've got some different scenarios going on, and we're going to compare these. In this first one, we have a distribution that started off right skewed. And remember, it's right skewed because it's got that right tail. And then also I want to show that we are starting with this information for the mean, median, and standard deviation. And so that's our original distribution. And then what I've done is I'm taking samples of size 2. So it's drawing samples from my original distribution of size 2. So it does this, draws two different ones, and you end up with all these different samples of size 2 from the original population. And I drew 1,000 of those. So 1,000 samples of size 2 from the original distribution. And what I end up with is this new distribution, the sampling distribution. So I took samples from the original, and this is now what it looks like, samples of size 2. Now you'll notice in the new distribution, the sampling distribution, that it's still slightly right skewed. And the mean is close but not exact. And then the standard deviation is an adjusted standard deviation. So some things that we do want to note here is that the distribution was right skewed. To start with. And then when we took samples of size 2, so n equals 2, then the sampling distribution was also right skewed. And our mean looks to be a little bit off. And then our standard deviation is approximated by population standard deviation over square root n. When you type that in, it's slightly different decimal wise. It might be like a rounding thing, or it might be some inaccuracies because of the sample size. But typically that's what you're going to do to find not typically, that is what you're going to do to find the standard deviation of the sampling distribution. So for the next one, we also start with a right skewed distribution. And you can see that right tail here. I took slightly larger samples of size 15. And now it's starting to take on a more normal size or normally shaped distribution. And if you look at the mean, that's a lot closer. And then again, our standard deviation is still found by this same formula. But you can see that with a larger sample size, our sampling distribution is less spread out. We're kind of narrowing in on this true population mean. So in the one to the right, we had a standard deviation of like 8. And in the one, the one on the left, we had a standard deviation of like 8. And then the one on the right, it's getting smaller. So it's kind of closing in on that population mean. So this one, we started right skewed again. We had sample size of 15, and then it's taking on a more normal shape with a smaller standard deviation. So hopefully in the next couple examples, you'll start to see how sample size is going to affect our sampling distribution. So on the next page, again, we have 2 right skewed distributions to start with. And then you'll notice on the left one, I've taken a sample size 30, which is large. It fulfills that technical condition of being a large sample size. And then in the one on the right, instead of 30, I did 60. So I doubled that sample size. And hopefully with the side by side, you can kind of compare what's happening with the shape of the distribution of the sampling distribution, which is the one on the bottom. And you can compare those standard deviations. We've gone from 2.17 to 1.5. So as our sample size is getting larger, our spread is getting narrower, actually. And we're also zeroing in on that true population mean. If you'll notice, our population mean was 14.05, and with a sample size of 30, we've got 14.05. So that's kind of a sweet spot. But in either case, we're starting with this right skewed distribution. And then when we do a sampling distribution and we take a large enough sample size and enough of those, we end up with an approximately normal sampling distribution, which is crazy. So I think it's crazy, at least. What's happening is we're normalizing this distribution, and it's helping us kind of narrow down what the true population mean is. And literally, our distribution is getting narrower. So in this one, it's getting like really tall and skinny. It's narrowing in. And then this one is a little bit more of a normal shape. So some big ideas here about this is kind of what I've mentioned, that you can start with a skewed distribution. And if you take large samples of the distribution and compile a sample of the samples, a sampling distribution, it takes on a normal shape. And let's see, let's kind of write that up. There's some questions down here. I want you to take what you've seen in these simulations, and I want you to summarize what you've seen, pause it, summarize it, come back and check it with me. Okay, I've summarized kind of what we've talked about. Basically, what's happening is if you start with a skewed distribution, when you take a large enough sample size, so greater than or equal to 30, then your sampling distribution will take on an approximately normal shape. And then what happens with the mean and the standard deviation as n gets larger is that the mean gets closer to the true population mean and the standard deviation gets smaller. And I did some symbolism here that I want to explain. It says, as n approaches infinity, which means gets bigger, comma, the sampling distribution standard deviation gets smaller. That's negative infinity, which is meaning gets smaller. And then as we take more samples of samples, is same thing, that we're getting closer to that population mean, standard deviation gets smaller, but what happens is our distribution takes on a narrower, gets taller and skinnier, narrower shape. So now let's look at a distribution that starts normal, and let's see how changing those numbers affects the sampling distribution. In this first example, we have a bell-shaped distribution, which is a normal distribution, exactly normal. Look at how perfect, how clean that is. And then I took samples of size 2, which is small. And we saw in the previous example that when I took samples of size 2, since it was small, we ended up with a skewed sampling distribution still. But in this case, you'll notice that even though we took samples of size 2, now I took a whole bunch of them. I should have reset that, but same idea will apply. Even though I took small samples, since we started normal, we've got this normal distribution. So let's just kind of explore here. I went and took larger samples, size 30, which is technically large. That fits that technicality of our qualifications. We still have this, normal shape, but it's getting narrower. And in this one, I only took 1,000, but it's okay because my sample size was large. So in both these cases, let's summarize what's happened. We start normal. N is small, but our sampling distribution, I'm going to abbreviate here to save time, is still normal. And then in the next one, we start normal, took large samples, and we have a narrower, still normal sampling distribution. I abbreviated. Hopefully you can still understand it. That's part of note taking. When you're in college, part of note taking is kind of abbreviating when you're writing a whole bunch, and in statistics, you got to write a lot, or like history anyway, rabbit trail, abbreviate. So let's look at some conclusions for this. Again, pause it, fill out your conclusions, come back and check it with mine. Hopefully you were able to write something close to this. It doesn't have to be exact, but as long as your main ideas are the same, you're good to go. So in summary, when you start with an exactly normal distribution, it doesn't matter the sample size or the number of samples, you're still going to end up with a normal, exactly normal, perfectly normal sampling distribution. So you start with normal, you end with normal. And the sample size didn't really affect that. What the sample size did affect was how narrow that distribution got. So we saw that when we had a technically large sample size, that our sampling distribution got taller and narrower, which means that our standard deviation got smaller. And then for the mean, I wrote as n approaches 30, or as n gets larger, our mean of the sample means is approaching our true population mean. So I wrote that in symbols. Hopefully you can tell what I'm saying here. The mean of the sample means is approaching the population mean. So what that's saying is we're getting closer to the true population mean. So if there were a scenario where maybe you didn't know the population mean, maybe the population's way too big, then we can use these methods to help us narrow down what the true population mean actually is. And we can find it without taking a sample from every single observational unit. I love this stuff. I think it's so exciting, which leads to the This is really important. It's a really big idea. All of this stuff is the backbone to this central limit theorem. And this theorem ensures that even though a population may not be normal or normally distributed, if the sample size is relatively large, which is greater than or equal to 30, then the sampling distribution will still be approximately normal. So all that stuff, all the pictures we saw, we can summarize into a theorem. So this is like concrete, for sure, math law, the central limit theorem, that no matter what kind of distribution we start with, if we take a large enough sample size and enough of those samples, we end up with this approximately normal sampling distribution. Very exciting stuff. So there's some really important things that we need to note about the central limit theorem and some things that need to happen to ensure that we can even use the central limit theorem. There's like some qualifications that you have to have before you can use it or apply it. The shape of the sampling distribution will be approximately normal. I'm sorry, I said this wrong. I said these were the qualifications. The qualifications is the next bullet. This is describing the central limit theorem. That's my bad. The center will be centered about mu, the population mean, and the standard deviation will be sigma over square root n. And then here's the qualifications. I'm very sorry about that. Here are the qualifications. The sample has to be randomly selected, which is why I used that simulator from the textbook, because it did true random samples from the population. The sample size must be large, or if it's not large, then the population has to be normal to begin with. This is so important. And regardless of the population distribution, if the number of samples is large enough, the sampling distribution will be approximately normal. So this is how I want to go back over this because I said it, I jumped ahead. This is how you're going to describe the distribution based on the central limit theorem. And then these are the qualifications that have to be met for you to apply the central limit theorem. So before you can even assume the things that we know from the central limit theorem, you have to make sure that the samples were randomly selected. You have to make sure that the sample sizes were large. And if they were not large, then the population had to be normal. And if you don't know anything about the population that you need, then you need to be very cautious about using the central limit theorem. And if you do continue to use it, then you need to state, we have to be cautious about our conclusions because these things were not met. So I have an example down here of how we can use this, how we can apply this, and if we can apply it. A variable has a population of mean 100, standard deviation of 28. So this is our population mean, and this is our standard deviation, population standard deviation. If the variable is normally distributed, and it doesn't say it, but we are going to assume that it's randomly selected. I should have put that in there. Identify the sampling distribution of the sample mean for samples of size 49. So what it's asking here when it says identify the sampling distribution of the sample mean, it's telling you to describe the sampling distribution. And so in order to describe the sampling distribution, we want to see if the central limit theorem can apply. And if we look at the information given, we have a population mean, we have a standard deviation, we know that the variable is normally distributed, and we have a sample size that is large enough. So the only thing that it didn't explicitly state was that it was randomly selected. But since the other ones were met, And since I typed this up, I'm going to go ahead and tell you that I meant to say that these were randomly selected. That's my bad. So since all those conditions were met, then we can go on to describe or identify the sampling distribution. For the sampling distribution, the mean is going to be the same as the population mean. The standard deviation is going to be adjusted by square root n. And then I'm going to simplify that. That turned out nice. And since the variable under consideration started normally, then that means its sampling distribution will also be exactly normal. So I'm going to describe this in words down on the bottom of the paper so I have some more room. And I'm going to say the sampling distribution is normally distributed, not approximately, because the original was normal, with a mean of 100 and standard deviation of 4. So if we go back up right here, we can identify the sampling distribution of the sample mean by talking about its shape, its center, and its spread. I forgot a word here. I think I forgot to finish that thought. So if you're writing notes, go back and finish that thought. I'm very sorry. Okay, then the next one, can you determine the sampling distribution of the sample mean for samples of size 16 if the distribution of the variable under consideration is unknown? Let's look back at our technical conditions that must be met. Go up here, technical conditions. Technical condition number 1 is that it is randomly selected. I stated in the previous example that they were, even though I didn't write that, I need to do that. Randomly selected, that's good. Sample size must be large. What is the sample size in this example? 16. So that's not met, but that's okay as long as the original distribution is normally distributed. Does it say that our population is normally distributed? No. So since we don't know and sample size is 16, then we cannot assume anything using the central limit theorem. We cannot apply the central limit theorem. So we'll just state that. Since the shape of the distribution is unknown and n is small, we cannot apply the central limit theorem and determine anything about the sampling distribution. So those are some big ideas from the sampling distribution and the central limit theorem. Just make sure that you read back over those technical conditions and make sure that those things are met before you apply it. But that is all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know and I'd be happy to help. See you in the next one.